Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, do I need to check the sound? Okay. So this is work done jointly with Minho Sung, who is another student at Georgia Tech, my co-advisor Jim Shu, and Jia Wang from AT&T Labs. So the problem we solve in this paper is the estimation of the probability distribution of flow sizes in the internet. In other words, for every positive integer, we are trying to estimate the number of flows that have that integer size, and the size here is in terms of packets. So this is the probability distribution we are trying to estimate. We look at a link for a particular measurement interval and count the number of flows of each particular size. And this is a plot on log-log scale, so you can see that there are 500,000 flows of size just 1. But as you look at larger and larger sizes, the number of flows of that size goes down very fast. And beyond about 100, you see very few flows of any particular integer size. So size is in packets. So there is a tremendously large number of flows with just one packet, and that number goes down exponentially. As you can see, this is a straight line on the log-log plot. So this is the distribution we are trying to estimate. Now, if we had per flow data structures, all we had to do was keep one counter for each flow, increment it whenever we see a packet, and in the end just sort the counter sizes, and we would get this distribution. But per flow data structures are very expensive, so that's why we have to go through all the motions that we go through in this paper to estimate this distribution. Now, in this work, we do not put any restriction on how you define your flows. A flow is defined as a combination of labels from the IP header, and you can specify, depending on your particular application, what fields from the header you want to consider in your flow label. And depending on this definition, the semantics of your measurement will be different. So if we choose the 5-tuple source and destination IP and port and protocol ID, then each TCP level, then it's equivalent to counting each TCP flow as a separate flow. We could also define the flow label as just the source IP. So all packets coming from the same source would be considered to be belonging to the same flow. So in some sense, this gives a generality to how you define your flow. So here's an overview of how I'll go through this talk. I'll begin with the motivation for the problem, briefly cover the related work, and then describe our system model. And we spent some extra effort on estimating the number of flows of size 1, because that's a especially interesting quantity, and I'll try to motivate why that's so interesting. And then a holistic approach that allows us to estimate the entire distribution of flow sizes. And finally, a multi-resolution extension that helps us handle the variability in number of flows. So why do we want to know the distribution of flow sizes? If we know the flow distribution, we can infer a lot of things about the usage of the network. So, for example, we could infer the access bandwidth of the user population. We could infer the application types in use from the predominant flow sizes in the links. It's even more interesting from a security perspective, because incipient worm infections or DDoS attacks, they show up as a huge explosion in number of flows of size 1. Because DDoS attacks, if you define your flow as the 5-tuple, then a worm that's spraying packets to random destinations, or a DDoS attack that's spoofing source IP, will appear to be sending a huge number of flows of size just 1, because each packet seems to be coming from a separate source or going to a separate destination. Route flapping, on the other hand, will shift some large flows from failed routes to newly set up routes. So a fluctuation in the number of large flows will indicate route flapping or other network anomalies. And then there are higher level applications such as estimating the traffic matrix that can build upon this mechanism as a, so that can use this mechanism as a primitive to estimate more interesting higher level network level quantities.
How can you estimate the access thing without duration?
So this mechanism runs in measurement intervals of a certain fixed time, which is a design parameter. So if you know the interval length and you know the flow sizes, then you can go back and infer the access bandwidth. So this problem has been explored in the past, mostly by folks from AT&T, because they are network operators and they started motivating this problem. The approach till now has been to invert the distribution obtained from sampling. So there are measurement boxes such as net flow, and what net flow does is it samples 1 in 1,000 or 1 in 5,000 packets and maintains per flow records for these sampled packets. Now, sampling introduces a lot of inaccuracies, especially for short flows, because if you are sampling 1 in 1,000 packets, then a flow that has less than 1,000 packets is going to show up as just a single packet sample, or maybe it will be missed out totally. And the general observation is that most of the flows in the internet are very small in size. So sampling misses out a huge majority of the small flows, and the ones that it captures, it totally distorts their estimated size. Because if you are sampling 1 in 1,000, if a flow of 500 packets contributes a single packet to your sample set, it's very difficult to infer, just looking at the sample set, what the original flow size was. There are also some mathematical limitations to inverting sampling, which have been shown by other researchers in previous conferences. So I'll go through our solution architecture, which does not use sampling. So we process each and every packet going through the network. Now, clearly we don't have time to update a per flow data structure, and neither do we have enough space to retain a per flow data structure if we have millions of flows going through the link. So we use a two-stage solution where we have an online streaming module which is updated for each packet. But this module, so this module has to run at line speed, and it has to be very simple, it has to be implementable in hardware, and it has to have a very, very simple processing, maybe just 1 or 2 operations per packet. Once the online streaming module collects measurements, it periodically ships them to an offline processing module, which is just a software application sitting on a box. And this processing module looks at all the measurements collected and infers the flow distribution from the measurements. So our solution basically is in 2 stages. The first stage collects information at a very high speed, and the second stage then processes that information to infer the final piece of information that we are interested in, which is the flow distribution. So the first module, which was the online streaming module, it's just an insertion module. You look at every packet and insert something into the data structure. And the data structure it maintains is very simple. It's just an array of counters accessed by a hash function. So it's not a hash table, because we do not try to resolve collisions. So all we do is, I'll show you a quick animation. We have an array of counters. A packet comes in, the processor computes the hash function and chooses a particular counter and increments that counter. Another packet comes in, the processor hashes the flow label again. This time it goes to some other counter and increments that one. A third packet, this time belonging to the same flow as the first one, comes in. So this time it will get hashed to the same counter, and the same counter will be incremented. Now a fourth packet might sometimes hash to the same location because of collisions in hashing. And we do not try to avoid this at all. So we do not try to resolve collisions. That makes our data collection very fast, very efficient, but also lossy, in the sense that it collects data which is not precisely what we wanted to collect. Now, implementing an array of counters has been studied by people, in particular George Varghese and SRAM Ramabhadran had a paper in Sigmatrix which did a very nice architecture for this. The idea is pretty simple. You maintain small counters of just 7 bits or so in fast memory and maintain a large counter in slow memory. And every time your small counter is about to go above a threshold, you go back and write back to the large counter corresponding to this small counter in slow memory. So it's a kind of caching, but instead of caching a small set of the large memory, it caches a thin slice of all of the large memory. So you have 64-bit counters in slow memory and 7-bit counters in fast memory, and the 7-bit counters write back to the 64-bit counters. So that's all this architecture does, and it perfectly fits the requirements for this application. So clearly the data collection that we have done is erroneous. It collects something that's not precisely what we wanted to know, which was the distribution of flow sizes. So now I'll describe the estimation module, which takes this array of counters and processes it to give out a bunch of estimates. And the interesting quantities are: one, the total number of flows; second, the number of flows with exactly one packet, because that's a especially interesting quantity; and the entire flow distribution. So I'll use these symbols for these three quantities: n for total number of flows, n1 for number of flows with exactly one packet, and phi for the entire distribution. And the observations that we have from the counter array are just these counter values. We don't have any other information than that. So we have counters with value 0, because some counters will be totally untouched by all of the packets. And then we have counters with other values from 1 to z, and we use variables y1 to yz to indicate those counters. So this picture tries to capture the distortion we get because of the collisions in hashing. So the red line is the actual flow size distribution. So if there were no, somehow magically if there were no collisions in hashing, then we would get exactly that in our counter value distribution. Unfortunately, that's not true, and as we have a hash function with smaller and smaller range, we get more and more collisions. So the actual distribution that we obtain from this array of counters is more and more distorted away from what the actual distribution is. So the green line, for example, uses 1 million counters, and this is a data set with about 1 million flows. So you can see that the green line is quite close to the red line, but there is a slight distortion. And notice that this is a log-log scale, so that distortion is quite huge actually. And as we use smaller and smaller arrays of counters, so 512k or 256k counters, we get a larger distortion away from the actual distribution that we are trying to estimate. So finally, our estimation mechanism has to have an algorithm that somehow takes this distorted distribution and gives us an estimate of the actual distribution. So that's what this mechanism is going to do. So let's first look at these two interesting quantities, the total number of flows and the number of flows of size exactly 1. So let's say there are m counters in the array of counters, and let's assume that our hash function hashes every flow label to one of these counters uniformly at random. So then we can model the number of flows hashing to any particular counter by the Poisson random variable with the parameter lambda equal to n by m. So you have n flows, m counters, and n flows hashing uniformly to these m counters. So the number of flows hashing to one of these counters is modeled by this Poisson variable. So this modeling gives us a simple estimator for total number of flows. If we know the total number of counters, which is m, and number of counters that have a value 0, which meaning the counters to which absolutely no flow was hashed to, then this formula m equaling natural log of n equaling m multiplied by natural log of m over m naught gives an estimate for the total number of flows that went through. So this result is actually quite old, and it was first published in 1990 by some database guys. And we extend this exact same model to derive another estimator that gives us the total number of flows of size 1. And the extra work here is using this Poisson variable. So this estimator was derived by just looking at the counters with value 0. Here we use the observation that counters with value 1 could only be caused by a flow of size exactly 1 hashing to that counter, and exactly one of such flows hashing to that counter. Because there is no other way you can get a counter of value 1. There has to be exactly one flow of size exactly 1. Counters of size 2 don't follow this kind of logic, because they could either have one flow of size 2 or two flows of size 1 hashing to them. But counters of size 1 all have this property that they have exactly one flow of size 1 hashing to them. So we just use this model to compute the probability of a counter having exactly one flow hashed to it, and then invert that formula to get this estimator for the number of flows of size 1 out of these total flows n. And this estimator turns out to be extremely accurate. Actually, our experimental results show that this estimator gives us within plus minus 1% of the actual number of flows of size 1. And this is an interesting result, because if you look at data collected via sampling, one of the examples is this trace that they collected at University of Colorado when the SQL slammer worm was spreading. And there were a huge number, so the number of flows of size 1 was 5 million, and 4.5 million of those packets, those flows, basically single packets, were these slammer worm packets, and only 500,000 were genuine flows of size 1. However, if you sample 1 in 5,000, then out of these 4.5 million, you only get about 900 samples. So in your sample flow distribution, you see a very small increase in the number of samples. On the other hand, the number of this estimator will give you a very accurate representation of this increase.
What is Y1 in the formula?
Okay, sorry. Y1 is the number of counters with value 1. So Yi in general is defined as the number of counters with value I. And if you observe closely, there is a dependence on the total number of flows that is derived by this formula here. So there is a dependence on all the previous estimates in this mechanism. So N1 is dependent on our estimate of N, because that feeds into the formula here. And if we try to derive an estimator for number of flows of size 2, N2, then that will depend on both N1 and N, and so on. So that's why this approach does not generalize for arbitrary I very easily, because as you get larger values, you could have many different combinations causing that particular counter value, and trying to extend it builds up all these dependencies on previous estimates. So all the inaccuracies kind of accumulate. So we'll not try to extend this technique further. We'll instead develop a slightly different technique to estimate the entire distribution.
Unrelated, but what exactly is that?
We are hashing the flow label. So let me just run you through the model once again. So basically we have these packet arrivals, and we hash the flow label, which is here. Yeah. So the flow label can be any combination of fields chosen from the IP header. So this is something that needs to be defined a priori, but this mechanism we have tried to keep it general. So you get to define what is the you get to define the flow label. You get to specify the fields of the IP header that you want to consider as the flow label. So for example, if you say, okay, my flow label is source IP, then all packets coming from the same source IP will be considered to be belonging to the same flow.
Then you get that information, correct?
Mhm.
And you assume that you have like one or
Counters. So these counters take very little space. More precisely, if we are operating in hardware, we use a counter architecture where each counter is implemented by 7 bits in SRAM and 32 or 64 bits in DRAM. On the other hand, if you try to store the flow labels, that takes a lot of space because your flow label can be anywhere from 4 to 20 bytes. And we have seen flows of, we have seen numbers like 1 million flows per second. Especially if you have these anomalous conditions such as a worm infection going on, then you'll see a huge number of flows of size 1 because each packet seems to be going to a different destination. So if you try to store all the flow labels, that will cost you a huge amount in storage. And like 20 megabytes or so per second, or even more than that. And even more complicated than just the storage is trying to maintain that data structure at line speed, because now you have something like a tree or even a hash table excuse me, which has a worst case access performance of log n, and you don't have time because you need this mechanism to operate at line speeds in very high speed networks. So you don't have time to excuse me, you don't have time to go through any per flow data structure and update the corresponding counter. So you want a mechanism that has really constant number of operations per packet. So our mechanism has just 2 operations: hash the flow label, go and increment the counter. That's it.
Why do you need to have an estimate for the total number of flows? Will you sum all the counters and that give you the total number of flows?
That will give you the total number of packets.
Okay, so that's it. Okay.
So that's clearly a slightly different quantity. Total number of packets is what you get from SNMP counters today. On the other hand, total number of flows is something that
One flow could have many packets.
exactly. And actually, just knowing the total number of packets and total number of flows already gives you things like what's the average flow size. So total number of flows is interesting but not obtainable by some straightforward mechanism. So now let me try to describe the estimation mechanism used to estimate the entire distribution. So the technique we use here is at a high level, it is a statistical technique used by people working in Bayesian statistics, and we actually found that out after we had designed the algorithm. So the algorithm, the intuition behind the algorithm is the following: you have an observation which is the set of counter values. So the distribution of counter values is what you have observed. What you really wanted to estimate was the distribution of flow sizes, but you don't have that estimate. So here's one way to compute that estimate. Take a guess of what the estimate could have been. Use that guess and your current observation to compute the distribution. Now this seems like a circular argument, because if you already knew the distribution, then why would you compute it? But the thing is that because your guess is not going to be perfectly accurate, using your guess when you try to compute the flow distribution, you will end up computing something slightly different. And a very trivial and slightly simplistic example of such a procedure is computing the root of equation fx equals x. You know, if fx is sin x, if you want to compute sin x equals x, one way to do it is pick a random x and take its sign, take the sign of the sign, and so on, and it will converge to something where sin x equals x. So that's the kind of intuition behind this mechanism. So we take a guess of the flow distribution, we take our observation, which is the counter value distribution, and we compute a refined estimate of the flow distribution. And we do this iteratively. So in the next iteration, the result of the previous iteration will be used as initial guess for the next iteration. And in practice, this converges very fast. So after about 5 iterations, we get an estimate which is within 2% of the actual distribution. So, and it turns out to be an instance of the expectation maximization algorithm. So in statistics, there is this idea that if you want to compute a certain quantity, and you have a particular observation, then you condition that observation onto a certain guess of that quantity, and do exactly what we are doing here. Iteratively refine your guesses and plug them in your computation to get a more refined guess. Plug that refined guess again into your computation to get an even more refined guess. And this process is guaranteed to converge. It is not guaranteed to converge to the right solution all the time. So that's something which we can only determine empirically. So we show in our experiments that it does converge to something very close to the actual distribution. So I'll give an example of how we use a guess of the distribution to compute a refined guess of the distribution. So let's just consider the counters of value 3. Now counter value of 3 could be caused by 3 cases. Either there was a single flow of size 3, or a flow of size 1 and a flow of size 2 both hashing to the same location, or 3 flows of size 1 hashing to the same location. Now if we somehow knew the flow distribution, we know the probability of a flow of size 3 existing in the distribution, probability of a flow of size 2 and a flow of size 1. So we can compute the probabilities of these individual events. And let's say the relative probabilities of these 3 events are 0.5, 0.3 and 0.2. And let's say we have seen 1,000 different counters in our initial counter table having a value of 3. Then we'll say that, okay, roughly a fraction 0.5 of these counters came from the first population, a fraction 0.3 came from the second population, and a fraction 0.2 came from the third population. That will allow us, so that gives us these numbers. 500 counters were caused because of a single flow of size 3, 300 were caused because of a flow of size 1 and a flow of size 2, and 200 were caused because of 3 flows of size 1 each. This reconstruction allows us to compute, so once we do this reconstruction for all counter values, so I've just shown this example for 3, but we do this for all counter values, then we get a new distribution of flow sizes, because that allows us to compute how many flows of size 3, 2 and 1 were there. So this is how our circular computation proceeds. We have an estimate, we use that estimate to decompose the counter values into various colliding flow sizes, and use that to compute the total number of flows of different sizes. That gives us the new distribution to use in the next iteration. Any questions at this point? So I'll now go over the results, and in this figure I have actually cleaned out the noise in this part of the figure, and the way I have done that is used bins of varying sizes and averaged the number of flows falling in those bins. So that's just to clean out the noise in the lower part of the figure, and that has nothing to do with the operation of the mechanism. So this is just a visualization trick to make the graph readable on the lower right hand side. So the red line is the actual flow distribution, the green line is the raw counter values, and you see a huge deviation towards the top left corner, which corresponds to small flows, because there are lots of small flows and they often collide with each other to cause a distortion in the observed values. And the dotted blue line, which actually totally overlaps with the red line, is our estimates of the distribution. So zooming in on the top left corner of this curve, we see that our estimates converge to something very close to the actual distribution, but for some local noise. And this is a correction which is about 2 orders of magnitude on the log scale. So these are some comparisons with what you could do if you were inferring from sampling. And so the black and blue lines correspond to curves where you would sample with either one packet in 10 or one packet in 100 and then try to infer the flow size distribution from your sample set. And the red line is estimation using our algorithm, and the gray line is the actual flow distribution. And gray line is actually totally overshadowed by our estimates, which means our estimates fall exactly on the actual distribution. And the same figure, but with the noise on the bottom right cleaned out by that bucketing trick. So you can see what's happening here is, even if you sample with a very high rate, 1 in 10, which is not something you get in today's internet, you still get just a very smooth sort of average of the actual distribution, especially towards the lower, especially towards the left end of the figure. So both these blue and black lines that correspond to inferring from sampling, they are just smooth averages of your actual distribution, and that is a serious loss of information, because whatever interesting phenomena you are going to see, for example, a spike in flows of a certain size or predominance of flows of a certain size, they are all going to show up only if you actually are able to follow the shape of the curve, and not if you just get a smooth average. So the actual flow distribution is totally overshadowed by the red curve, which is our estimates. So they totally coincide. If you, I guess if you look really closely, you see these plus signs that correspond to the gray curve, and the red boxes, which are our estimates. And this is about, in terms of matrices, we have a metric for quantitatively looking at the accuracy of estimates, and our estimates turn out to be an order of magnitude better than the estimates inferred from sampling. And this is sampling 1 in 10 or 1 in 100. In today's internet, in practice, we get sampling 1 in 1000. The best we get is about 1 in 1000. And the very high speed routers are not able to do that, so they give you 1 in 4 or 1 in 5000, something like that. This is another data set which is DNS traffic, and again you see that the variations are captured much more closely by our estimation. So here there is a bit more distortion on the right side, so you can see the gray and red lines are slightly apart sometimes.
How are you getting the ground truth?
So we have the entire trace. So this is a simulation experiment. We have the entire trace, so we can get the precise answer. Then and actually this is the same data set used by our predecessors. So we just took their results of what they got from sampling. So they did a sampling over this set and then tried to infer from the sampling. And we run this trace through our mechanism and then infer from our mechanism. So one problem with this solution is that if you have a spike in the number of flows, then you will start occupying a lot more counters. So let's say you had 500,000 flows, and suddenly your number of flows go up by a factor of 10 because you have a DOS attack or some sort of worm infection going on. Then your number of flows go up drastically. And because your array of counters is fixed in size, your distortion will increase if your number of flows increase. So that's the same figure I showed a while ago. So one way to read this figure is that if you have a smaller number of counters, then you get a larger distortion. Another way to read this figure is if your number of counters stays constant but the number of flows increases, then the distortion will increase. This figure shows how our iterative estimation mechanism converges with number of iterations. So if we have a very good, relatively less distorted initial data point, then we converge very fast, and actually even after 5 iterations we converge to very close to the actual distribution. On the other hand, if we start with a hugely distorted data set, for example something like this, then it takes a lot of time for this mechanism to converge. So what's really happening here is that as the number of flows changes, we really need to have provision for the worst case to make sure that we are able to converge fast. But that's a sort of waste of space, because if we provision for the worst case, then we are over provisioning by a factor of 10 or so for the average case. So a solution for that is using a multi-resolution array of counters. So what we do here is we think of a virtual array of counters which is very, very large, which is large enough to accommodate the worst case number of flows that you could ever see on your link. But don't implement all of those counters. Implement a much smaller array of counters and do it in the following way. Cut up your large array of counters into 2 slices, then cut the smaller slice again into 2, and so on. So slice it up in these exponentially decreasing sizes, and fold up each of the slices into a actual array of counters which is much smaller. So the largest slice here is about half the total size, and you fold it up r times, so that its size decreases drastically. So what this corresponds to is that you take all the flows hashing to anywhere in this portion and you increment a corresponding counter here. So 2 raised to power r minus 1 counters here will map to just a single counter here. So that corresponds to a very large portion of the flows will map to just a narrow end of this array. This other extreme is where every flow going to this part is hashed to a corresponding counter here. So instead of implementing all of your virtual array, you implement one end of this array, and the rest, the remaining portions, you fold them up by different proportions and implement just those folded portions. So what this gives you is, so now the operation of the mechanism is as follows. You get a packet, you hash it to a virtual array, it hashes to somewhere in this array, and you go to the corresponding counter here and increment that one. So flows that hash to this end, they'll all have a unique counter for themselves. So they'll all be accounted for at a very high resolution. Flows that hash somewhere here, they'll actually get folded up to a single counter. A lot of flows here will all get hashed to a single counter. So here we have a very coarse granularity measurement. And all of this is running in parallel because a flow will hash to only one of these locations, and we implement all of this together. So this gives us a multi-resolution version. So in data collection we don't have to worry anymore about the total number of flows, because we run this mechanism and we collect data at each of these resolutions. But when we try to do the estimation, the first thing we need to do is estimate the total number of flows and use that estimate to pick just the right resolution for the rest of our estimation. So that allows us to estimate the distribution with the most pertinent resolution and get the least degradation in estimate quality. Did I get this?
That was part of your EM algorithm.
Yes, but we had a standalone estimator for that, right?
Oh yeah.
So we could run that for any of these chunks and then just scale it up to account for all of these. And we actually, so for that particular estimator we have a very clear notion of what's the best, most accurate estimate. So each of these chunks will have different occupancy levels, clearly. If we have just a few flows, then this chunk will be very lightly occupied. On the other hand, if we have a lot of flows, then this chunk will be almost completely occupied, because a huge number of flows are anyway folding up. So we want, this estimator actually has a sort of convex accuracy plot. So the estimator works best when you have just about 50% or actually 63% occupancy in terms of number of counters. So the idea is something like this. If you have just one counter that was occupied, then that's going to give you very rough estimates because you saw very little. If almost all the counters are occupied, then again the estimation goes wrong because you have a huge distortion. And if just the right proportion of counters are occupied, then that's where you get the best operating accuracy.
So 63% is like 190%.
1 minus 1 over E. So there are these final two curves which show that our multi-resolution mechanism works for very different total number of flows. So we have this trace with 50,000 flows and this trace with 500,000 flows, and both the traces run through the same configuration of the multi-resolution give us very accurate estimates. So the red line is actual distribution and green is what we estimate using the multi-resolution mechanism.
So, I just,
Sure.
so you first try to estimate the number of flows, and
Yes.
you choose how many, how big M,
Yes. So
how many M of those phases you want.
So we first choose the resolution that was occupied just correctly to give us the most accurate estimate of n, which is the total number of flows. So because each of these will give us an estimate of n, but one of these will be the most accurate, and we know how to identify that. Once we know that, we use that particular array to estimate the entire distribution. So let's say we pick this one, then this only corresponds to a small fraction of the total flows. We estimate the distribution for this and then augment with the observations in the rest of the arrays. So we do not throw away the rest, but we scale this up and augment it with the outlying observations in the remaining arrays to construct the final estimate.
What's the number of flows? What's the number of flows?
Mhm.
What's the size of
So this mechanism gives you the distribution, but it does not give you the size of an individual flow.
the distribution of this number? Not the distribution of the number.
So there are two separate questions you could ask. You could ask, okay, this is the flow label, what's the size of the flow? So that's one question. The second question is, what's the distribution of flow sizes? I don't care about individual flows. So this mechanism is answering the second question. The first question is slightly harder to answer, and we actually have a separate paper that answers that question. So we have a separate data structure that does it, and there we have a approximate probabilistic answers. So we answer it with we give approximate answers which are correct, which are within plus minus epsilon with a very high probability. But that's a mechanism that's totally independent of this architecture. So to conclude, I presented a data streaming based solution for estimating the distribution of flow sizes. We call this, so at an abstract level, this is an instance of data streaming, because we have this data stream which is the packet headers, and we have limited memory in our hardware, and we want to process the stream and answer queries. And the queries that we are answering here are of the nature, what's the distribution of flow sizes. So this is an instance of data streaming, but with very networking centric perspective. And the technique was to use a lossy data structure for data collection and then use Bayesian statistics to invert the collision process and get an accurate estimate of the actual distribution. And this gives us an order of magnitude improvement over sampling based estimation mechanisms. And the multi-resolution version allows us to trade off between how accurate estimates we get and how much storage we want to use. Because clearly if we had unlimited storage, then we would just operate the entire virtual array instead of operating those small physical arrays. Thank you. Yes, that is a quick answer. Yes, we are also saving on computation, because even if we had a lot of, if you leave out the extreme case where you have infinite memory, then of course your hash function lets you access a unique counter without any probabilities of collision. But other than that abstract notion, you always have these bad cases where you have to use chaining or something else in your hash table. So even if you had a lot of memory, you'd still need some extra computation to access a particular location in the hash table, compare the flow label of the current flow with the flow label that you have for the node in the hash table, and then do something special if you detect a collision. So all that would cost you in terms of computation, and there is some sort of a real-time constraint when you are trying to process packets at line speed, because you don't have time to just go and do the worst case once in a while, because that worst case could occur in the middle of a lot of packets coming through, and you really need constant time behavior for computation.
The rates you're talking about, you have to go out of computation. You start to have that well. And it's like,
So computation does become a problem, not because you don't have fast enough processors, but because there is more functionality you want in any sort of monitoring processor that you will have on your line card. You want more functionality than just this. And so in terms of computation, the problem is not really just the arithmetic or floating operations, but the memory access operations. So because you need to, each of these nodes in your hash table, you need to read them off the memory and then write back to them, and that ends up being the bottleneck, because if you are doing log n memory operations in the worst case, then you have the memory latency for those log n accesses to account for. Yes, but so usually you have in the hardware architecture that you have for processing packets at line speeds, your packet header really comes on the fast path. So in some sense you have done all the specialization to process packet headers at high speed, because that's what you really designed your hardware especially for. So they usually have a gig E or faster port on chip, or usually it's on chip or just off chip on the board, and they have a special bus, so it's not even your PCI Express or anything like that. They have a special hardware bus just to shift the packet header very fast from the port into what your processing code. So getting the packet header across is not a bottleneck, because that's clearly something you will have to do anyway if you are going to process packets at line speed. On the other hand, if you are going to do all these memory operations, and then you have to do a bunch of other things too. So if you are going to do packet forwarding on the side and things like that, so you anyway have a lot of operations for them. One question?
So in an order sense, if you have like n flows, how many, what is the size of the counter you require to be at a certain accuracy level?
So usually when you have n flows, we need order n counters, because we can compensate for collisions, but really if we go below 50% of below half n, then the collisions the distortions start becoming too much, and the convergence of the estimation slows down. So
I never really did counter with 7 bits and then say if you have million flows, then like it is quite big. It's not like,
you are talking about the counter width, not the number of counters.
I'm talking about the number of counters.
The number of counters, right? So that's why I had the multi-resolution mechanism, because that allows you to not implement a lot of counters.
Yeah, but I mean, even if you do a multi-resolution counter,
So in multi-resolution, you really need just a constant, or basically log n, but log n with a huge constant factor, so the constant dominates there in practice.
but I mean, there is an issue with the how much accuracy you have in the estimation of the counter.
Yes, yes.
I mean, if there are 500,000 flows and you have like 1,000 counters, what would be the accuracy?
That would give you very bad estimates. My guess is 500,000 flows and 1,000 counters would tell you the sizes of the largest few counters, but beyond that it would not give you much information.
So what would be the optimal number of counters?
So if you are not doing the multi-resolution, then to accommodate 500,000 flows you need more than 250,000 counters. So something like 300,000 or something like that. On the other hand, if you are doing multi-resolution and we worked out a particular configuration that we used in these experiments. So that configuration had 198k counters, 64k times 3, that many counters, and that accommodated all the way till 500,000 flows without any problem.
And then you have a lot of number of flows, reset, never have effect,
So yes and no. Yes, because ultimately that's what we are doing too. Our measurement also proceeds in intervals, and at the end of each measurement interval we flush out the counter values. Now what you are suggesting is do this at keep a per flow data structure and flush it out whenever it gets full. So in the worst case, that degenerates to just tracing packet headers. And so that is clearly not an option, because your packet headers are going to overwhelm your disk bandwidth. So disk bandwidth is something like
we have certain number of counters, and that's enough for whatever the reduction rate. So you need to keep your equipment cannot handle all the headers, but can handle 1 million of the traffic, then you design of the counter just to handle 1 million of whatever you know.
Okay. So just to make it slightly simple, if we continue to talk about the worst case, so I know that this is a slight exaggeration, but in the worst case, if every packet belongs to a separate flow, then what you just proposed will, in the limit, what will happen is because each packet belongs to a separate flow, your buffer will fill up at some point, and then you'll have to write it off to the disk while packets keep coming. So if you look at the throughput of this system, it has to be as fast as the packets are arriving.
No, this one, the next one, the thing that set up UTL hierarchical,
Mm-hmm.
same way. What you're trying to solve is this mode resolution algorithm. To solve that, well, I have no idea how much. So I'm saying that even on that solution, which is like big, no mode resolution, and using your, you think you
Mhm.
and flush at a time that varies according to how much flow I have.
Okay. I'm sorry, I misunderstood your question. So, yes, so the effect of what you are proposing will be that why not shorten the measurement interval instead of trying to do something special to accommodate more, and that is clearly one possible solution. And there is really just this trade-off that if you shorten the measurement interval, then you are not using your counter array very efficiently, because most of the time you will be running much under what you are. In some sense, you are just over provisioning for the worst case. You are saying, okay, let's look at the worst case and let's have our measurement intervals such that even in the worst case, the counter array will still be able to accommodate the packet flow. So that is a valid solution, and we could do that. It would just mean that we would be over provisioning by a factor of 10. So
That is not varying interval, it's not fixed interval, but varying the interval just like the varying the resolution or varying the interval.
I actually think the opposite is like you will over-provision by whatever the number of operations is interval detail. Because like one of them has this information, other ones have like marginal interval. And by changing the interval, you actually swap the swap that has that whatever this one that has maximum.
Isn't that, you can't measure anything, any flow longer in duration than the interval you use.
so there's the trade-off that if your interval becomes really small, then your granularity goes too fine. So you then need to start worrying about composing these informations, because exactly as you pointed out, that's clearly one of the problems, that if your measurement epoch is too small, then you just answer questions about very small intervals. Also, what will in general happen is that packets in networks do not have pure random arrival processes. They have TCP, for example, has a very periodic thing. It sends a bunch of packets, waits for a bunch of acts, and sends a bunch of packets. So if you look at simulations of TCP, you will see a bunch of packets going. So there is this cyclic kind of behavior, and if you do not capture these cycles, so if your measurement interval is not large enough to capture these cycles, then you will miss out on some of these characteristics that occur at time scales which are larger than your measurement interval time period. Thanks for sharing that.
What's the initial size of flow? Is like number of packets or is it the
Number of packets.